For thousands of years, we have looked up in the night sky and asked some pretty big questions. What's our place in all this? How did it even begin? We were a species lost in the sea of cosmic questions. What if I told you that the answers to some of the universe's greatest riddles weren't found just by looking up? They were found by running some of the most clever and mind bending experiments. So, today we're going to take a journey to uncover the 8 pivotal experiments that unlocked the secrets of the universe. Let's start with something that shapes our daily lives, the seasons. For centuries, people figured Earth was closer to sun in the summer and farther away in the winter. And it made sense, right? But it's totally wrong. In fact, if you live in the northern hemisphere, our planet is actually closest to the sun in the middle of winter. The real answer is way more elegant and was pieced together over centuries. The secret isn't the distance, it's the tilt. Earth doesn't sit perfectly straight. It's tilted on its axis by about 23.5 degrees. As Earth takes its year-long trip around the sun, that tilt means that half of the year the northern hemisphere is angled more directly towards the sun, and for the other half, it's angled away. So, when your part of the world is tilted toward the sunlight hits more directly, like a focused flashlight beam, heating things up. And that's summer. When your hemisphere is tilted away, that same sunlight comes in at a shallow angle and spreads out, which gives us a colder days of winter. A simple tilt is the engine of our planet's season, a mystery that was solved not by one single moment, but by centuries of patiently watching the sun's path across the sky. What are stars made of? For most of the history, stars are just lights. What they were actually made of was the question for myths, not science. Were they divine fires, celestial diamonds? Nobody knew. That is until 1860s when two scientists, Gustav Kirchhoff and Robert Bunsen, unveiled a game-changing technique, spectroscopy. The idea is both simple and brilliant. When you pass the light in a flight through a prism, you get a rainbow, a spectrum. But Kirchhoff and Bunsen found out that if you heat up elements until it glows, it doesn't make a full rainbow. It emits lights only in specific sharp lines. Each element has its own unique color barcode. Now they realized that the dark line others had seen in sun's spectrum were just the opposite. Elements in the sun's atmosphere were absorbing those same specific colors. By matching the dark absorption lines from the sun to the bright emission lines of element in their lab, they could finally figure out what stars were made of. And the result was stunning. The stars weren't made of some magical celestial substance, they were made of same stuff as Earth. Now, decades later, Cecilia used the same very method in what's often called as the most brilliant PhD thesis in astronomy history to prove that the stars are mostly hydrogen and helium. A clever experiment with light finally revealed ingredients of the heavens. What causes the phases of moon? Moon's ever-changing phase is one of the most familiar sights in our night sky. But for ancient cultures, it was a puzzle, a total puzzle. Was it God changing its mood, or was it being eaten and reborn every month? The explanation were all over the map. The truth, which was actually figured out by ancient Greek astronomers like Anaxagoras way back in 1428 BC, is all about geometry. The moon doesn't make its own light. It's just a giant dusty mirror reflecting the sunlight. The phases we see are just our changing view of the moon's sunny side as it orbits the earth. When moon is between us and the sun, the side facing us is in shadow, a new moon. As it moves, we start to see a sliver of that sunlit side, which gives us a crescent. When the earth is positioned right between the sun and the moon, we see the whole sunlit phase, a full moon. The phases weren't just a change in moon itself. It's just a cosmic dance of earth, moon and the sun. This simple, elegant idea, later confirmed by telescopes, replaced thousands of years of myth with cosmic clockwork. What is the nature of comets? Before science got its hand on them, comets were terrifying. These hairy stars would just show up unannounced, blazing across the sky. They were almost seen as bad news, omens of war, death, and disaster. Most of the people thought that they were just disturbances in the atmosphere. That all changed in 1705 thanks to English astronomer Edmund Halley. Using his buddy Isaac Newton's shiny new laws of motion and gravity, Halley started digging through old records of comet sightings. He noticed that the comets from 1531, 1607, and 1682 had suspiciously similar orbits. He made an incredible and bold prediction. These weren't three different comets, but one single comet that kept coming back every 76 years or so. He wagered that it would show up again in 1758. Now, Halley didn't live long enough to see if he was right, but on Christmas night of 1758, the comet appeared, right on schedule. It was named in his honor, and his prediction proved that comets weren't random omens but predictable members of our solar system, playing by the same rules of the gravity as everyone else. Now, we later learned that they were just ice, dust, and rock, dusty snowballs. And in 2014, the Rosetta mission actually landed a probe on one, giving us a close up look at these frozen leftovers from the birth of our solar system. We have gone through some terrifying omens to predictable dirty snowballs, and the discoveries only get bigger from here. If you're digging this journey through cosmic history, do us a favor and subscribe and hit that notification bell. We have so many more mysteries to unravel together. Now, back to the science that shaped our world. What causes tides? If you have ever been to a beach, you have seen one of the Earth's most powerful forces at work, the tides. For centuries, the daily rise and fall of the ocean was a complete puzzle. Some people thought that it was Earth literally breathing. Observers noticed a connection to the moon early on, but nobody could explain why. The answer finally dropped in 1687 when Sir Isaac Newton published his masterpiece, the Principia. The force responsible, he explained, was gravity. Moon's gravity is always pulling on our planet. It's not strong enough to do much to solid ground, but it has a huge effect on the liquid oceans. The water on the side of the earth facing the moon gets pulled the hardest, creating a bulge. That's the high tide. And here's the genius part. The solid earth itself is pulled more than the water on the far side. This leaves the water on the opposite side of the planet behind, creating a second bulge. As our earth spins through these bulges each day, we get two high tides and two low tides. And Newton's laws turned the mysterious breath of the ocean into predictable and elegant dance of physics. What is the source of sun's energy? For a long time, the sun was a huge scientific paradox. Geologists and biologists knew that the life and the earth processes needed millions of years to unfold, so the sun had to be ancient. But how? If it were a giant piece of burning coal, it would have turned into ash in few thousand years. If its heat came from a slowly shrinking under its own gravity, it would last only few tens of millions of years. The sun's incredible lifespan just didn't make sense. By the way, did you know that Jupiter actually shrinks a little bit, like 1 mm per year, and that what causes energy inside Jupiter, and that energy is more than what it gets from the sun? The answer had to wait for 20th century and the birth of nuclear physics. In 1939, a physicist named Hans Bethe, building on earlier ideas, finally cracked the code. He laid out the exact mechanism that powers the sun, the nuclear fusion. Imagine, by 1939 we had discovered a lot of things but did not know what stars were made of. Crazy. Now, deep inside sun's core, the pressure and the temperature are insane. We're talking here millions of degrees. It's so intense that hydrogen atoms are slammed together with enough force to fuse into helium. But here's the magic trick. The new helium atom has just a tiny bit less mass than the hydrogen atoms that made it. That lost mass isn't gone. It's converted into massive amount of energy, exactly as described by Einstein's famous equation E equals to mc square. Now this process, happening billions of times a second, is what has kept the sun shining for over 4 billion years, and it's what will keep it going for billions more. What is the structure of solar system? For over 1400 years, the Western world had one official model of the universe. Earth was the center of everything. The sun, the moon, the planets all circled around us. It was elegant, it was intuitive, and it was completely wrong. The revolution started with a quiet bang in 1543. A Polish astronomer named Nicholas Copernicus suggested a wild idea. What if the sun was at the center? He argued his heliocentric model was mathematically cleaner, but he didn't have enough definite proof to convince everyone. That proof would come from the next generations of astronomers, most famously Galileo Galilei. When Galileo pointed his new and improved telescope at the sky in 1610, he made a series of discoveries that shattered the old worldview. He saw that Jupiter has its own moons, which proved that not everything orbited Earth. But the real smoking gun was Venus. He observed that Venus goes through a full set of phases, just like our moon. This was flat out impossible in Earth-centered model. Only way you could ever see a full Venus is if it was on the far side of the sun. That single observation was the nail in the coffin for geocentric model, proving that Earth wasn't at the center of the universe, but just on the planet going around the sun. What is the origin of the universe? Now, this is the big one. Where did all of this come from? For most of human history, this was a question for creation myths, not for science. Scientific answers seemed impossible, but in 1920s, astronomer Edwin Hubble made an observation that changed everything. Hubble discovered that pretty much every galaxy he could see was moving away from us, and even weirder, the farther away a galaxy was, the faster it was moving. The universe was expanding. Now, this idea has a mind-bending implication. If you could rewind the clock, everything in the universe must have been closer together. Rewind it all the way back, about 13.8 billion years, and you get to a single moment when everything was packed into unimaginably hot, dense point. This was the birth of the Big Bang. But a theory this big needs evidence. The smoking gun arrived in 1965, completely by accident. Two radio astronomers, Orzo Penzias and Robert Wilson, were trying to get work done, but they were being driven crazy by a faint, annoying hiss in their antennas. Now, it was coming from every direction, day and night. They tried everything to get rid of it, even cleaning out the pigeon droppings from the equipment. Finally, they realized they hadn't found the noise. They had found the answer. That hiss was the cosmic microwave background, the leftover heat from the Big Bang itself. It was the afterglow of the creation, an echo that still fills the entire universe. From the tilt of our planet to the afterglow of creation, every one of these discoveries was a major leap for humanity. Each of them started as a mystery, something to be feared or explained with myths, and ended with a deeper understanding of our place in the cosmos. It shows us that the universe, as big and as wide as it seems, isn't unknowable. Its secrets are waiting for us, written in the light of distant stars and laws of physics. And here's the best part. The journey is nowhere near over. For every answer we find, we uncover a dozen new, even better questions. That's the beauty of science. Now, it's a tool that not only gives us answers but empowers us to keep asking, to keep pushing, and to never ever stop looking up with a sense of wonder. Thanks for watching.